everyone. This is a video that, in a very simple way, would like to answer the question, what is energy? Energy can be a kind of vague term sometimes that's thrown around a lot, but we're going to look at it from a physical science perspective. And there's a number of ways you can define energy, but we're going to be using the definition that energy is the ability to do work. And now that's the scientific meaning of work, right? We talked about work before, that work is force times distance. Okay, so work and energy are very similar. They're very closely related. Okay, so we can break down energy into two main types. Okay, over here we can call this, let's see, stuff that can move. It doesn't mean it's moving. It's stuff that has the potential to move. So it's called potential energy. So for example, if you have a force applied to something but it's not moving a distance, we know it's not doing any work, but energy-wise, it still has energy. It just has potential energy. It's not actually moving yet. Okay? Our second type, say stuff that is moving. All right, and the word we use for stuff that is moving, and we've encountered this term before, is kinetic. Okay, so we have potential energy. That's stuff that has the potential to move with a force applied. And kinetic energy is stuff that is moving. Now, any object with energy has either kinetic or potential energy or some combination of the two. The potential energy plus the kinetic energy of an object is the total energy. All right, and the total energy is important because of a very important rule. We've talked about this rule, I believe, and we've talked about similar ones. It's the law of conservation of energy. And what the law of conservation of energy tells us is that energy is never destroyed. Another way of saying that might be that energy into a system has to equal the energy out of a system. Okay? The amount of energy that's in a system is still going to be there. Like it has to come out the other side. Energy doesn't just disappear. It can change forms, which we'll talk about later in this lesson, but it never disappears completely. It's always somewhere. So it could change from potential to kinetic or kinetic to potential, or it could be a little bit of both, but the total energy is still going to be the same. Let me see if I can give you a little bit of a better picture of that. Okay, and we'll talk about the formulas in just a minute too. So let's say I draw us, give you a little picture here as best I can. Excuse my lines, they're not always straight, but just draw us a little diving board here. And maybe get us a little water at the bottom here. Let's give us some numbers to work with here. Let's say that the diving board is 2 meters tall. Now, what I'm going to do is I'm going to clone this a couple of times so I don't have to draw it again. You'll understand why in just a second. And all right, now I'm going to come up here and I'm going to add us a little diver. And this first one right here, our diver is going to be standing on the edge of the board here. All right, there's our little diver getting ready to dive. And we're going to say he has a mass of 50 kilograms. That's our diver, okay? And just for the sake of simplicity, we know that the acceleration of gravity is 9.8 meters per second squared, but we're going to round it, and we're going to say gravity is about 10 meters per second squared, just to keep the numbers simple for a minute, because that's not it's not going to be that important to us, the numbers right now, just the concept. So right now, this guy is above the ground. He has a force acting on him. That force is gravity, of course, but he's not falling, so there's no motion involved. He's not doing any work. However, he does have potential energy. And his potential energy, we could find his potential energy by we take the force applied to him, which is his weight, which is his mass times gravity, right? And we can multiply that by how high he is off the ground, by his height. So in this case, he's 2 meters off the ground. Okay, so his height. So our numbers here, his mass is 50. Gravity, we said we're just going to round it to 10. And his height is 2. So in this picture right here, his potential energy is 1,000. Oh, we hadn't talked about the units yet. We use the same units as work. We use joules. Okay? Told you work and energy are closely related. So we use the same units. They're joules. His potential energy is 1,000 joules. All right? Moving down, let's say he's jumped off the platform at this point. Okay? All right, he's left the platform. He's falling. If we assume he's fallen a total of 1 meter, then we go back to our little potential energy formula. Remember it. We did mass times gravity times his height. In this case, his mass hasn't changed. He's still 50 kilograms. Gravity is still the same. It's still 10. But now he's only 1 meter from the water. So his potential energy is 500 joules. All right, and down here, we'll just give him a big old splash down in the water here. Now he splashed down in the water using the same formula, potential energy equals mass times gravity times height. Okay, his mass is still 50. Gravity is still 10. and his height is 0, which means his potential energy is 0 joules. Okay, so he's went from 1,000 joules of potential energy to 0 joules of potential energy. Now we just said the law of conservation said energy is never destroyed. It never just disappears, so it had to go somewhere. Where did it go? Well, if you notice right here, he's not moving. So his kinetic energy, the energy of his movement, is 0 joules. In this one, he's moved halfway down. Oops, there should be an E. All right. Half of his energy has been converted from potential to kinetic. So it's 500 joules, his kinetic energy. And in this case, he's reached the bottom. So all of his energy has been converted to kinetic, to movement, from non-movement. So his kinetic energy is 1,000 joules. So his total energy, remember, total energy is potential plus kinetic. His total is 1,000 joules in all 3 cases. The amount of energy has not changed. It just has not, the amount has not changed. The type has changed. It went from potential to kinetic, but it has not changed the total. Okay, so there's a couple of formulas you can get out of this. All right. Kinetic energy. The formula for calculating kinetic energy is 1/2 mass times velocity squared. Okay, and you can write that formula down. There'll be some problems where you'll have to solve using this formula. Kinetic energy is 1/2 mass times velocity squared. This example I gave you, I didn't tell you the velocity. You're not at a point where you could calculate the velocity, so don't worry about it. Potential energy. There's lots of ways to calculate potential energy. One of the most common that you're going to encounter this year is when gravity is involved. Gravity, the force of gravity is pulling something down and it could possibly fall. And we just talked about that one several times. It's mass times the acceleration of gravity times the height or the distance that it's going to fall. Okay, it's the same for calculating work. Force times acceleration, or mass times acceleration is the force times the distance. Okay, is related to the formula for work. So potential energy. The other thing I want you to get out of here is that kinetic energy plus potential energy is the total energy. All right, total energy does not change. Total energy must be the same because of the law of conservation of energy. All right. So when energy transforms, it doesn't just transform between kinetic and potential. There's different forms of energy or the different forms that energy can take. And we're going to talk about 7 of these real quick. So the first one is one that you're probably the most familiar with. It's real easy to think about. You just draw a little picture here to represent each one. In this case, let's say that's a little nut. Not like the kind you talk about the kind you screw in like a bolt, right? And we'll represent this with a wrench. All right, and that wrench is moving because this is mechanical energy. Mechanical energy. Okay, and that just is the energy of things that are moving. Whenever something moves, it requires mechanical energy to make it move. Okay, so that's energy of moving things. Sort of like kinetic energy, right? All right. So, what's another form that energy can take? Well, energy can take the form Okay, let's draw us a little flame here. It's a little log on fire. That's actually a couple of types of different energy we could talk about, but we're going to use this for chemical energy. Now, chemical energy, we've talked about chemical bonds. If you remember, ionic and covalent and metallic bonds, okay? These bonds store energy, and when that energy is released, that's chemical energy. Okay, it's energy that comes from ionic, covalent, and metallic bonds. A good example is burning wood. Okay, the cellulose in the wood, that's a bond, right? That's a covalent bond, cellulose. It releases that energy when you combine it with oxygen, and that's what gives us fire. Okay, so that's chemical energy. It's energy that comes from ionic and covalent bonds. A third type of energy, and this one shouldn't be too hard to remember. Electrical energy, right? And that, here, I just put us a little lightning bolt here. Electrical energy, that's easy to remember because we use it every day. And energy, electrical energy comes from the flow of electrons. Okay, the flow of electrons moving from one place to another. Remember, that's why metals are such good conductors of electricity, because in metallic bonds, the electrons float in kind of a loose sea. They're able to flow very easily. That's why metals are such a good conductor of electricity. So electrical energy comes from the flow of electrons, and it can be stored as potential energy, or when it's actually flowing through the wire, that's kinetic energy, right? Because it's moving. So electrical energy comes from the flow of electrons. Okay, a fourth type of energy is nuclear energy. All right, in nuclear energy, I'm sure you guys are very familiar. Yes, we have like nuclear plants and nuclear plants. All right, here's me draw a little mushroom cloud here, right? There we go. Nuclear energy, that's probably what you're most familiar with. You know, it comes from the nucleus of an atom. That's where the word nuclear comes from. It's the nucleus, okay, the atomic nucleus. So yeah, the protons, the neutrons, all right, in the middle of an atom, that they store a lot of energy in their together in their nucleus. When it is split, there's two ways you can obtain nuclear energy. You can split the nucleus. That's called fission with an I. That's what you get when you get the atomic bomb, not the H bomb, but the atomic bombs that were dropped on Hiroshima and Nagasaki. They came from splitting the nucleus of an atom, fission. Okay? You can also combine nuclei. So you can combine two hydrogen atoms to make helium, and that's fusion. And that energy is what powers our sun. Okay, so those are two types of nuclear energy, fission and fusion. Make sure you don't mix those two up. All right, let's see. 3 more to go. The next type of energy is thermal energy. And thermal energy is better known as heat. All right, and it comes from the movement of molecules. We talked about the kinetic theory of matter, how matter is made up of molecules, and these molecules are constantly in motion. Well, that's what thermal energy is. It's the movement of those molecules, right? So, kind of a cheesy little thermometer over here. It'll help us a little visual reminder. Here's some mercury down in the bottom. Right, it goes up. Thermal energy, that's heat. All right, and another type of energy is electromagnetic. Okay, that's just a fancy word for what is better known as light. Now, when I say light, I don't mean just the visual light. Sometimes we humans we get stuck in thinking what we see is what there is, right? But light is much broader than what we can see. Okay, radio waves, yeah, like the radio waves that bring your TV, bring your on your cell phone. Those are a form of light. You can't see them, but that doesn't mean they're not a form of light. We just can't see every type of electromagnetic wave. Radio waves, microwaves, okay, X-rays. These are all forms of light, forms of electromagnetic energy. All right, so make sure you keep that in mind, that when we say electromagnetic energy is light, we're not just talking about the light you can see. Although I can kind of put a little light bulb here, and there you go. There's a little reminder for electromagnetic. And then finally, we have sound waves. Okay, sound. So sound is vibrations that move through a medium. I mean, it means they have to travel through something. They can travel through water, they can travel through wood, they travel through the air all the time. That's how we hear each other talking. Okay, but they can't just travel in a vacuum. Thus the tagline from Aliens, "In space, no one can hear you scream," because air can't travel, or sound can't travel without something to travel through. Light, on the other hand, electromagnetic rays, they can travel through space. They don't need a medium to go through. Sound, however, does. So these are 7 forms of energy. And so going back to the law of conservation of energy that says, we can't destroy energy. This is sometimes why it seems like energy just kind of disappears. It's because it changes form. Okay, when you think about gasoline, gasoline has potential energy. It is chemical energy. The bonds in gasoline have potential. Whenever you burn gasoline in your vehicle, you're going to produce mechanical energy. It's going to turn your engine, right? It's going to be changed from chemical energy to mechanical energy. However, it's not just mechanical energy. If you measured the mechanical energy coming out, it would not equal the potential energy of the gasoline. So did energy disappear? No. Some of the energy is transformed into thermal energy because engines get hot too. Now, if you could take the thermal energy and the mechanical energy and all the different types of energy and add them up, then it would come out to be the same. So when it seems like energy is disappearing, it's not really disappearing. Most likely it's just been changed into one of these 7 forms of energy. Okay? I hope you guys understand the 7 types of energy and that this lesson makes good sense to you. Okay? So watch out for the next video, and in the meantime, good luck.